Welcome back to another lesson. In this video, we'll kick it up a notch and discuss two-dimensional tensors, which can essentially be thought of as matrices with some number of rows and some number of columns. One typically deals with 2D tensors when working with grayscale images, since as you might be aware, a grayscale image is simply a two-dimensional matrix of pixels, each pixel's intensity denoted by a numeric value that ranges from 0 to 255. Such that an intensity value of 0 indicates no intensity, something being completely black, and 255 representing something of maximum intensity, something being completely white. We can store this two-dimensional grid of values. We can store these grayscale images as 2D matrices. That being said, tensors can be extended to 3 dimensions, 4 dimensions, and so on. So on a new Jupyter notebook, we will import torch and initialize a tensor 1D is equal to torch.arrange. And what arrange will do is initialize a 1D tensor. And we'll have that tensor go from the number 2 up until the number 7. Outputting 1D, it returns a tensor that goes from 2 to 6. Which makes sense since the stop integer is exclusive. This is very similar to the range function that you would see for a Python list. Similarly, one can include a step size of 2, which specifies the gap between each pair of points. In this case, the gap is simply 2. Let us remove the step size, and we'll have the one-dimensional tensor go from 0 up until a stop integer of 9. We will begin by viewing this one-dimensional vector form as a two-dimensional matrix, such that 2D is equal to 1D dot view, and we want to view our matrix to have 3 rows and 3 columns, outputting the result of 2D. And it seems that we got an error, which simply means that I have to rerun this cell and then this one. And we obtain our two-dimensional matrix. We can confirm the dimensionality of this matrix by checking the number of dimensions. 2D dot dim. And it returns the number of dimensions to be 2, a two-dimensional matrix of 3 rows and 3 columns. Let us now look at how we can index or slice two-dimensional tensors. Suppose I wished to access the number 0 from our 3 by 3 tensor, located in the first row, which would correspond to index 0. You know what, let's leave this as is and do this on a new cell, 2D at index 0. Columns in this case are indexed from 0 to 2, such that our number 0 is also in the first column, column 0. Outputting this returns the expected value of 0. The value 5 is on the second row, third column, therefore on row 1 and column 2. So if we try to index that, 2D at row 1, column 2, outputting the value results in the number 5. We will now kick it up a notch and create a new tensor, x is equal to torch dot arrange, that will contain 18 elements with a start integer of 0. You can include your start integer of 0, although by omitting it, it will be inferred as such. And I wish to view this tensor dot view as a 2 by 3 by 3. This should work once again since 2 times 3 times 3 yields 18, and outputting this tensor x. Notice that now it's 3-dimensional, such that there are 2 blocks, and each block has 3 rows and 3 columns. The best way to think about this is imagine an Excel spreadsheet with 2 sheets, and each sheet has 3 rows and 3 columns. Alternatively, we can reshape our one-dimensional tensor into a 3 by 3 by 2 tensor. Printing this out, we get 3 blocks of data, each one with 3 rows and 2 columns. What I want you to take from this is our ability to change the shape of our tensor according to a tuple of integers. So long as that new shape of that tensor, its new dimensions must be compatible with the array's data. If I tried to put 4 columns per block, that wouldn't work. It throws an exception, since 4 times 3 times 3 does not correspond to 18 elements. It corresponds to 36 elements, in which case it would work. Now we can proceed into the slicing and indexing of multidimensional tensors, and we'll do that in the next lesson.